Good morning or afternoon, ladies and gentlemen. It is my great honor to be here today to present my work entitled Advances, Bottlenecks, and Future Prospects of Antimatter Storage and Control Technologies. My name is Chen Junwei from Dalian Ocean University. To begin, let me briefly introduce the concept of antimatter. Antimatter can be regarded as the mirror of matter. It has the same mass but the opposite charge. When matter and antimatter meet, they annihilate each other, converting almost 100% of their mass into energy. Because of this unique property, antimatter holds enormous potential in areas such as energy, space, propulsion, medicine, and fundamental physics. However, there is also a crucial difficulty. Storing it safely without annihilation remains one of the greatest challenges. Now, let us look more closely at its potential. In energy research, antimatter promises the highest energy density known, far greater than fission or even fusion, making it a candidate for the ultimate field. In space exploration, antimatter propulsion could enable interstellar missions with unprecedented efficiency. In medicine, positrons are already used in PET imaging, and in the future, controlled antimatter beams may provide ultra-precise cancer therapy. Finally, in fundamental physics, antimatter experiments are essential for testing CPT, symmetry, and exploring the role of gravity on quantum systems. The history of antimatter starts with Dirac's theoretical prediction in 1928, discovered the positron in cosmic rays. Today, antimatter is mostly produced in high-energy accelerators. For instance, high-energy gamma photons can transform into an electron-positron pair through pair production. Yet, the defining characteristic of antimatter is its annihilation. Once it encounters ordinary matter, it instantly converts into pure energy, usually in the form of gamma rays or emissions. This extreme instability is at once its most powerful feature and its most serious obstacle. Therefore, to make use of antimatter, scientists have developed several methods to capture and confine it. The three main approaches are the penny trap, the magnetic bottle, and cooling and storage systems. First, let us consider the penny trap. This device confines charged antiparticles, such as antiprotons and positrons. By combining a static magnetic field with an electrostatic potential wheel, the magnetic field provides radial confinement, while the electric potential prevents escape along the axis. Together, they form a stable three-dimensional orbit. And CERN, this method has already enabled researchers to capture antiprotons and even antihydrogen for minutes at a time, which marks a milestone in antimatter physics. Next, for neutral antimatter like antihydrogen, penny traps are insufficient. In this case, scientists employ a magnetic bottle, which uses regions of minimum magnetic field strength. Particles with magnetic moments are reflected back and forth, staying confined without touching the container walls. Although this technique enables non-contact confinement, it requires extremely strong magnetic fields and suffers from low efficiency. making it an ongoing technical challenge. Even if antimatter can be trapped, it also must be cooled to reduce its kinetic energy and prevent escape. Two main cooling methods are used: electron cooling, where cold electron clouds gradually reduce the energy of antiprotons, and laser cooling, which is highly precise and has been successfully applied to antihydrogen, combined with ultra-high vacuum and cryogenic traps. These methods have extended storage times from just seconds to several hundred hours. Nevertheless, the systems are still limited in capacity, extremely expensive to maintain, and inherently risky. In fact, stable storage requires extreme laboratory conditions. We need a vacuum below 10 to minus 12 torr and temperatures close to 1 Kelvin. Under these conditions, magneto-optical traps can suspend particles away from the walls, preventing annihilation. Such advances have already enabled experiments and CERN to hold antiprotons for hundreds of hours. However, the capacity is still very small, only about 10 to 4 particles, and the cost of operating such system remains extremely high. This brings us to the main bottlenecks that continues to limit the field. First, production efficiency is extremely low, with the cost of producing 1 gram of antimatter estimated at billions of dollars. Second, storage time and capacity remain insufficient for practical applications. Third, the systems are technically complex, requiring simultaneously maintenance of ultra-high vacuum, cryogenics, and strong magnetic fields. And finally, there are safety risks. Any failure of confinement could cause destructive annihilation. Looking toward the future, several promising directions may help overcome these bottlenecks. Advances in nanomaterials and superconductors could enable more precise magnetic confinement. The integration of AI and quantum control may allow real-time feedback and dynamic stability in storage systems, and multi-stage cooling, combining electron cooling with laser cooling, could significantly increase the density and lifespan for stored antimatter. Although these ideas remain at an early stage, they provide a clear roadmap for future research. In conclusion, antimatter represents one of the most extreme yet most promising frontiers of modern physics. From its theoretical prediction to experimental breakthroughs, we have advanced from instantaneous creation to controlled storage lasting hundreds of hours. Despite this achievement, its practical application is still limited by low efficiency, small capacity, high cost, and safety risks. Nevertheless, with future progress in material science, intelligent control, and cooling technologies, antimatter may one day revolutionize energy systems, space exploration, and fundamental physics, reshaping not only our technology but also our understanding of university itself. Thank you very much for your attention. I look forward to your questions and the stimulating discussion. Thank you very much.